Okay, we are moving on to 8.3, trying to make sense of some of these infinite series, whether or not they converge or diverge. And we've got two tests here. We have an integral test and we have a comparison test in this section. To start off, problem number 5 in our book wants you to focus on the difference between b to the n and n to the b. And so it's worth mentioning that if you look at this case, this is our base number and it's just being multiplied n number of times. So this is really the classic geometric. And in any geometric series, we need to pay attention to what that base number is. The base has to be less than 1 or greater than -1, or you could say the absolute value of the base has to be less than 1. If it's 1 or greater, it just explodes up to infinity, but if it's less than that, you're taking a fraction of it each time and it's getting smaller and smaller, so it converges under those conditions. Alright? In this case, n to the b, well, that's like we're saying 1 over, well, I guess we're saying 1 to the b plus 2 to the b plus 3 to the b dot dot dot. And it doesn't take a brain surgeon to realize that those are just getting big quickly and going to infinity. So we're more interested usually in the case of 1 over 1 to the b and 1 over 2 to the b and 1 over 3 to the b and so on. And that's what you call your p-series. And in this case, as we talked about last time, the critical thing is when that exponent is more than 1. If it's just 1, it's a harmonic series, and that is the famous, it goes to 0, each individual term disappears to 0, but the sum of them is infinite. But when you get more than 1, so when b, in this case, phrased like this, when it's less than -1, or in the denominator, when b is greater than 1 as an exponent in the denominator, it will converge. Okay, and we will see an example of this in a second. So let's try it. Here we go. We have a function that we can model this with. That would be f of x equals 1 over the 5th root of x, or x to the minus 1/5 power. And to decide what this is going to do by an integral test like we're asked to in the book, we would say, well, that's just going to be the integral from, we'll go from 1 to infinity for x to the minus 1/5 power. It's improper, so that's going to give us this in limit form. Well, I guess I'll write it like, we will write the limit, let's say as t goes to infinity, okay, when we take this integral, that becomes 4/5, right, because this is going to be x plus 1 up here, gives us, that gives us, 4/5 up there, so then I reverse this, this is 5 over 4, caught myself again, and then this is going to be from 1 to t as t goes to infinity. So just keeping, this is sort of the way you do improper integrals, right? It's possible to be a little bit sloppy on this and get away with it, but I don't encourage that sort of behavior. We have then 5 over 4 t to the 4/5, then minus, and we plug in 1, we just get 5/4. Okay, well, what happens as t goes to infinity? Well, as t goes to infinity, this goes to infinity, and the whole thing diverges. Alright, so this is divergent because that is going to infinity. The individual terms will go up, get bigger and bigger and bigger. Okay, so then now on to this one. We've got 1 plus 1/8 plus 1/27 and so on. We can write this in sigma notation, n equals 1 to infinity, and it's a very simple 1 over n to the 3rd. Alright, so that is just the classic p-series. 3 is bigger than 1, so it diverges by comparison to the famous p-series that we talked about. In 14, not too different, just to show that when you have some of these skills and understanding, these problems should go quickly n equals 1 to infinity. This then becomes 1 over n radical n. And again, if I wanted to write it in function notation, it would be n to the negative 3 halves, right? Well, that is, right there, that is the absolute value of that, in our p-series, it is less than negative 1. Negative 3 halves is less than negative 1, so this also diverges. That exponent down below is, oh, wait a minute, that is larger, so it converges, 1 over n to the 3 halves, that is larger than 1. So it converges. I can't talk and think at the same time. Sorry about that. Okay, let's see if I can try better here. This one we're asked to do in 25 by the limit comparison test. And what that means is we got a real sense of intuition that this is very, very close to 4 to the n over 3 to the n. And by comparing it to this, I can see if there's a constant, then something that we know diverges, and the comparison test links it to that, then this one will converge or diverge if this one converges or diverges. All right. So what you do is you just simply make a ratio. You'll say, all right, 1 plus 4 over n over 1 plus 3 over n all over 4 over n over 3 over n. Okay, what does that equal to? Well, I just flipped the fraction. I should have saved myself the time writing this. And I flip that to be 3n then over 4n. And then I can just swap these, and I can divide this into that and into that. And so this becomes 1 over 4 to the n plus 1. That's the numerator. And then times, now I've got 3n over 1 plus 3n when I've swapped places. And if I multiply top and bottom by 1 over 3n, then that just becomes 1 over, well then this becomes 1 over 3 to the n plus 1. So I have just reworked this, and now this is the limit as n goes to infinity. Okay, well this just goes to 0, and this goes to 0, so that's 1 over 1 goes to 1, and 1 times 1 equals 1. So when you compare these two things, these two limits, and they converge and they approach a fixed number, that links these two, so whatever this one does, the other one does as well. And in this case, what happens? Well, that's pretty simple. That's 4 over 3 to the n. That's larger than 1, just like we talked about up here. When b is larger than 1, it diverges, so this diverges. And that's the long-winded explanation of what you can really tell pretty much just by looking at this, that the 1s are of course not going to be very important, and you can ignore them and then just look at this, and that's where you are at the very beginning. So that's the fast way to do that. I hope that wasn't chopped off. All right, have a look at it there. So then